Welcome to Cascode Amplifiers Part 2. In the first part, we have actually seen the basics of Cascode Amplifier, and we considered one resistive load Cascode Amplifier. We come almost to the end of the design of a Cascode Amplifier with a resistive load. So let us continue with the same thing in second video. So in this, we have considered the same example. You can see this is the resistive load. In the previous video itself, we have actually found out what is the dimensions of M1 transistor and M2 transistor, which constitutes a CS amplifier and a CG amplifier respectively. And we have considered a RD of 500 ohms, and we have considered a drain current of 1 milliampere. Since it is 1 milliampere and 500 ohms, so since we are assuming a VDD of 1.8, we'll have a drop of 500 millivolts. We'll have the output voltage swinging at around 1.3 volts. So we'll see, of course, we have actually seen what is the dimensions of W by L of second transistor also. And this gives, by substituting the values of different values of ID, kappa and W by L, we can find what is the transconductance of M1. Which happens to be 9.98 millisiemens, and since we know, since we assume the value of lambda as 0.01 volt inverse, R01 happens to be 100K, and from which we can find out the intrinsic gain of CS amplifier happens to be 998.9, almost close to 1000 volt per volt. So we will see what is GM2. GM2 is almost close to GM1. There's a small, it is 9.98, here it is 9.96. Again, R02 and R01 are same because we assumed lambda of both the transistors as 0.01. So if we can actually find out, okay, what is the open circuit cascode amplifier gain, it happens to be 995.42 kilovolt per volt. So this is a huge gain. Since we have, even though A0 square is kilovolt per volt, since we have a resistive load which is of hardly 500 ohms, so if you can actually substitute all those values, the actual gain happens to be hardly 5. So you can see, okay, the open circuit, the cascode gain, which is almost 1000 kilovolt per volt, which is almost 1 megavolt per volt, has been dropped to almost 5 volt per volt, which is around 14 dBs. So we'll actually see the simulation of the same thing, same design in LT Spice, and try to understand, okay, how does this is happening. Friends, you can see now we have actually constructed a a cascode amplifier with a resistive load of 500 ohms. So this R1 and R2 and R3 are used to give that 0.6 volts. You can see we have a VDD of 1.8, and this will actually make the gate to source voltage of M1 happens to be 600 millivolts. And you can see now we assume the VDS sat of M1 happens to be 0.2. So that 0.2 plus again VGS of 0.6. So the V bias of this happens to be 0.8. So we have these values, and you can see W by L of first transistor, second transistor have been listed here. You can actually find out what is the dimensions of each of the transistors. We'll just see it now. The dimensions of first and second transistors as per the design is 249.5, and this is 248.262. So you can actually find out what is the dimension that we have set. You can see the length is chosen to be 10 micron, so naturally the width happens to be 2495 microns. And similarly we have the dimensions of M2, again length is 10 micron chosen, and we have the dimension of the width of M2 as per the requirement. And now you can see the model file have been defined for NMOS and PMOS with kappa as 200 and lambda as 0.01, and threshold voltage is 0.4. And for this it is minus 0.4. Only difference is kappa is 100 for PMOS. Whenever we, okay, this we have put, okay, considering simulation of the active load transistor also. So let us try to simulate now. I have applied an AC signal, so you can see AC of 1. So let me just run it and try to find out. Okay, we are expecting a gain of around 14 dBs. So I'm trying to find out what is the frequency response of this. So now we can see this is the frequency response I'm looking at. So you can see this is the frequency response. Let me change the color of this if it is not properly visible. Now this is fine. If you can see what is the gain, so gain you can see this is around 13.97. so this is what is it we were supposed to get. The design also we are getting. Let us just verify what is the design value. So you can see this is the design value, so which is 13.96. so we actually have the simulated value as 13.97, so which is fairly very close to the expected value. So let us this way we can able to simulate a cascode amplifier with a resistive load. So let us go back to presentation and try to find out. Okay, so now let me just proceed with active load cascode amplifier. Now you can see this is again the same cascode amplifier, but the load is being now replaced by the resistive load is now replaced by an active load. M3 is a PMOS transistor. So since it's we are looking this as a load because both source and gate are connected to DC voltage, and looking towards the drain, this will offer a resistance of R0. So to be very specific, it will be R03. So that's what is there. We are trying to analyze its AC analysis. So all DC voltages are replaced by AC ground, and you can see now since both source and gate are AC grounded, the effective of course M3 will be look like, okay, it will look like it will effectively act like a resistor, that is R03. Now we are trying to find out what is the cascode amplifier gain with R03 as the load. So if you can see here, of course we again go back to the same concept of replacing the cascode amplifier by its equivalent circuit with AV0 into Vin, where AV0 happens to be the open circuit cascode amplifier gain. So Rout dash is nothing but the resistance, okay, output resistance of the cascode amplifier, and RL in this case now it is R03, that is in the previous case as we saw, this is R03 now. So now we can actually get an expression for output voltage, which is this voltage multiplied by RL divided by the sum of the resistance, that is Rout dash plus RL. So since Rout is R01 plus E0 into R01, so as we saw in the previous case also. So if you substitute all these things, so since this A0 into R01 is far greater than R0, so this overall gain of this cascode amplifier with A0 with R0 as the load happens to be simply A0. So where A0 is the intrinsic gain of CS amplifier. So to conclude, the amplifier, cascode amplifier with active load as R0 will have an overall gain of A0. So let us go back to the same design, So let us consider the same values as we considered in the previous case. Let VDD be 1.8, let the overdrive voltages be 0.2, and let the current be 1 milliampere. So by considering the since we didn't change the values of lambda, Kp and threshold voltages and the overdrive voltage as well as the current, the dimensions of M1, M2 remains the same as it is written over here. So the bias voltage is also, again, it is 0.6 and this is 0.8, I have written here. But the dimension of M3, which is exactly acting like load, since the Kp of this is half of that, it has to allow a current of 1 milliampere. The dimension of M3 happens to be exactly twice of M1. That's why you can see it is written as 499, which is exactly twice of 249.5. And the bias voltage, that is VGS required for this, happens to be minus 0.6. Since we are considering VDD as 1.8, so if it is 1.2, I will get a VGS of this PMOS transistor, which is M3, is minus 0.6. So that's why VB3 is at 1.2. So with these values being set, so we are supposed to get a gain of around 997. So the actual gain in terms of dB happens to be almost 6 dB. I'll show you just in a moment. I can just show you the gain. This is the gain of an amplifier in volt per volt, which is 997.9. So in terms of dB, it is almost 59.98 dBs. So let us do the simulation of this. Again, we are considering a cascode amplifier with load R0. Now it's an active load. So let us do the LT-SPICE simulation and try to understand, okay, what is, how does this will have a gain of almost A0. Now let us see the simulation of cascode amplifier with R0 load as it was mentioned in the design. So we have replaced that our resistive load by a PMOS load. If you can see here, the PMOS load which is connected with V bias 2. So V bias 2 is having a bias voltage of 1.2, which will give a VGS of minus 0.6, and this is 1.8 volt, and this is 0.8 for this V bias 1. If we can actually see what is the dimension of this particular transistor, which is 499, should be the global ratio. If you can see here, this is 10 micron is length and 4990 is the width, and of course similarly we have the dimensions of M1, M2. So as per the design, so I have listed the dimensions of M1, M2 and M3. Again, we try to, of course, we can actually find out what is the gain of this amplifier, so which happens to be of 59 dBs. So let me run this and then try to find out what is the gain of this. So since I'm looking at only this, let me take out this. Okay, now we are looking at what is the gain. So of course we are supposed to get 59.94. We are almost having 60 dB. So this is the amplifier, cascode amplifier with the R0 load. We are expecting almost 60 dB. We are getting 60 dB gain as the gain of cascode amplifier with R0 load. So this way we can able to simulate, design a cascode amplifier with R0 load and verify the design. We will see next cascode amplifier with cascode load.